Thank you. So this idea of a harmonic oscillator. All right, and I want to talk a little bit about what this is. All right, what we're gonna do, and this is a problem. This is the kind of approach that we will take in this class. Is we're gonna want to understand something about a molecule or an atom, some sort of behavior, some sort of property, and we're gonna look for an analog for that problem in classical physics. Right? We're gonna think about balls and springs and orbits and things like that. We'll try to understand how things work from that perspective, and then what we'll do is we'll what they call promote the theory and the physics to quantum mechanics, okay? Which is, we're going to think about this idea of a harmonic oscillator, and in fact, we're going to realize that it's basically the same thing as a slinky or a taut string that you strum, right? Like a piano wire. Very similar physics to this. So we're going to have this idea, we're going to have these strings, and then we're going to want to make them quantum mechanical, little microscopic springs. Okay, and this is going to be our representation of a chemical bond, at least part of it. And so if we can understand how a spring works in classical physics, then we can understand, when we take it to quantum mechanics, how it works microscopically. Right? Because all we need to do is solve the Schrodinger equation. But in order to solve the Schrodinger equation for our system, we have to come up with a Hamiltonian. Right? We have to come up with a formula for our total energy. So what we'll do is we'll look at the total energy, or the physics of a spring in the classical world, and then we'll promote that theory by writing a Hamiltonian for it and solving the Schrodinger equation. All right, we'll do that next week. This week, I just want to identify the problem, and if we get through everything just fine, we'll actually be able to write down the Hamiltonian at the operator that represents our system, and then next class we'll solve it, and we'll come up with the wave functions for this magical spring. So the system I want to look at, this is in some ways the first truly chemical model. All right, I kind of hand-waved why the particle in the box was relevant in chemistry, and it is relevant in chemistry, but here you're going to see the connections to chemistry much more clearly, because we're going to be talking about chemical bonds for the next 2 weeks, how they act. All right, so what is a chemical bond? I'm not going to answer that question for you precisely. You know what a chemical bond is. But let's just set up our problem. So what I'm going to do is I'm going to take a diatomic molecule. All right, so that's a molecule of 2 atoms. Right? And I'm going to connect them with a bond. All right, I'm going to say those 2 atoms, which are drawn as circles here, have 2 different masses, M1 and M2. Okay, they could be the same atom. They could be different atoms, it doesn't matter. Right? But they have 2 different masses that may be the same. And what I want to think about is if I take this molecule and I take its bond and I stretch it, right? Or I compress it, either way. And now I get an extra long molecule. Right? The question is what's the physics of this, right? What's the energy of this process, right? So what are some questions we can ask about it, right? What are the physics of this stretch, of this motion? Right? What's the potential energy? What's the kinetic energy? Right? Those are the questions we need to ask, right? Because ultimately what we have to do is we're going to be doing this motion of stretching a bond and changing a bond, and we need to ask the question, right? We always have to write an operator down for the energy, right? Which means we need to know what the total energy of this is, the physics. And the first thing we need to ask is, well, what happens when you stretch a bond? Right? So when you take a classical object, you have 2 balls, and you put a slinky between them or something like that, or some stretchy material that connects them, and you stretch it and you let go, what happens? Right? How does this system evolve in time? All right, and so what are the characteristics here? Well, we have, so what are the things in our system? We have 2 masses, and we also have a stretchy bond. Right? We have something that's connecting the 2 atoms, that we can stretch or compress, right? It has some tensile strength. All right? So we need to think about what happens when we stretch a bond or we compress it. What happens to it, right? What does that motion look like? All right, and then when you start to think about this chemically, there's two different things happening when you stretch a bond, make a bond move, right? Because there's two different components physically in the bond or in the molecule, right? There are the nuclei, right? The majority of the mass in this molecule are not the electrons, right? It's the nuclei themselves, right? You got these. Imagine this is uranium. Right? You have uranium and oxygen, right? 99.9999% of your mass are the nuclei, right? So you have this motion of these really, really heavy nuclei oscillating with respect to each other, these big balls, but there's also electrons moving between them, right? Remember that if this is a covalent bond, what is a covalent bond? Well, it's a region between two atoms where electrons are being shared between them. We'll try to define that more explicitly when we talk about bonds and molecules later on. But there's two different types of motion here, right? There's the nuclear motion, and there's the electronic motion, right? If you stretch the bond, the electrons, when they're shuffling between the two atoms, if you think about them shuffling, now they have a longer distance to shuffle. On average, they're further apart from each other. Right? So there's two effects, right? And the problem is that, let's say we move the nuclei, right? The electrons are going to do something different at a new distance, right? They're going to have some new environment, and they're going to equilibrate and relax to that. Right? But I could also hold the nuclei together, fix them, and then stretch the electrons apart from each other too. So when I talk about a bond stretching, we have these two effects: electronic motion, electronic stretching, if you will, and nuclear stretching. And so we have to say, well, does that mean that our stretching our bond, do we have to deal with both at the same time? Right? So the question is, are these coupled? Does the nuclear motion affect the electronic motion, right? If I move the nuclei, does that really radically affect the electrons, or vice versa? Right, so the operative question here is, are these motions coupled? Do they relate to each other? All right, because if they are, well, then we have to deal with them together, right? If we stretch the bond, then we have to consider how the electrons move and the nuclei move, right? So if you have two nuclei and 100 electrons, well, that's a big problem, right? You have physics for 102 objects. Right? That's a tough thing to do. We know we can do it. Quantum mechanics allows us to work on that. It gives us a prescription. We can write down a Hamiltonian and solve it. Nothing's stopping us from doing that, but it's a hard problem. We got 102 things to deal with. But what happens if they're not coupled? What if the nuclei move at a different scale, in terms of time or speed or energy or whatever, from the electrons? In the sense that the nuclear motion is independent from the electronic motion. Right. Now, if that were the case, if they're uncoupled to each other, right, the nuclear positions don't really affect the electrons on the same time scale, then we can deal with them separately. We can move the nuclei and then worry about the electrons later. Right? Now the question is, of course, which is valid? And I have an answer for you. We're not going to formalize this until we get past the hydrogen atom, because it's kind of hard to see it until we really start to talk about atoms. But there's an answer to this question. And the question is that these motions are not coupled. We can approximate them to be not coupled. That the nuclei move in some ways independently of the electrons that are around. Right? And so the answer is, in fact, if you say for most molecules, up to about 1 part in 1,000, sometimes more, sometimes less, it depends on the molecule, these motions are independent. All right, So we can worry about the electrons independently from the nuclei. All right, so if the nuclei, if we're stretching that bond, we're moving the nuclei apart from each other, we don't really have to worry immediately about what the electrons are doing. All right, and I want to formalize that. I'm going to give you, instead of giving you the exact definition, the formal definition of this approximation, I'm going to give you a visual idea of how electrons and nuclei function together in a molecule by doing a typically corny Professor Cypher joke. I have a corny way to look at this, but it's a useful way to look at it. All right, so this approximation is called the Born-Oppenheimer, named after J. Robert Oppenheimer approximation. All right, this is work that Robert Oppenheimer did with Max Born during his PhD work. This was Oppenheimer's PhD thesis. And it's, in some ways, one of the most important approximations in all of chemistry. And what the Born-Oppenheimer approximation says, basically, is that the time scale of electronic motion, right, the average speed that electrons move at, how fast do they move, right? So what I mean by time scale is if you think about you've moved your bond, how long does it take for the electrons to relax versus the nuclei? So the time scale of the electron motion is much, much faster than the time scale of nuclear motion. So what do I mean by that? Well, if you look at, you can define this spectroscopically. If you excite an electron, and with your molecule of light, you excite the motion of an electron, and you ask the question, how long does it take for it to relax? Right? You give it some energy, how long does it take to come back to the initial state, to equilibrate? And the relaxation time for electrons is on the order of 100, let's say 10 attoseconds. That's 10 to the minus, let's say roughly 10 to the minus 15 seconds to 10 to the minus 12 seconds. Okay, so you excite an electron, you have it do something, and when does it equilibrate back to the starting position? It's about a femtosecond, really, really fast from starting point of view, right? So it's a very, very short amount of time. And when you stretch a molecule and you have it vibrate, which means the nuclei are moving, the time scale for that well, it's anywhere between, let's say, 10 to the minus 12 to 10 to the minus 9 seconds. Right? It's about 1,000 times faster. The electrons move roughly 1,000 times faster than the nuclei. That should make sense because the ratio of the proton mass to the electron mass is 1,000. The proton is 1,000 times heavier than the electron, so it moves roughly 1,000 times slower. Pretty straightforward. All right, so what does that mean? Well, the way that I like to think about nuclei in a molecule and electrons in a molecule is like an elephant. Now, I'm going to draw a really, really poor elephant for you guys. Here's my big trunk, my big feet. Big feet here. Here's my square elephant. The tail. Big floppy ears. Some eye and a big trunk. Really crappy trunk, right? So here's my elephant. Let me fix that trunk. I really do not like that. All right, there's my elephant. All right, and the elephant represents the nuclei. All right, so you got this big, heavy, lumbering object. Very important. Don't get me wrong, I love elephants. But it's a big, lumbering, heavy object that moves slow. And what are the electrons on the scale of the elephant? Well, the electron are just the flies buzzing around. Let me color the flies differently. All right, so you've got, you know, every elephant outside's got some little flies buzzing around it. Probably some around its butt. You got these little flies, right? And these are the electrons. Right, so you've got this big, humbling nuclear structure. They're moving. Of course, the nuclei are free to move. The elephant can do all sorts of things, but it's always got flies buzzing around it. And by and large, the flies don't bother the nuclei or the elephant. Right? They're always there. They're just buzzing around. Occasionally, a fly will land on its nose or its ear or in its eye, and it'll piss it off and it'll flick it off. You know. But by and large, the flies act as if, right, they just sit around the nuclei, you know, eat crap and eat little specks of dirt off of the elephant, you know, and lay its eggs on the elephant or whatever flies do with elephants. But by and large, the elephant doesn't care, right? It only is weakly perturbed by the flies. Only occasionally is it annoying, right? And this is exactly the way molecules work. Nuclei will move around with respect to each other all the time. And they're wobbling and vibrating and all sorts of stuff. And by and large, the electrons are just moving around so quickly around the nuclei it doesn't even notice. Okay? Well, we can formalize this mathematically. And when we talk about a molecule as a whole, with electrons and nuclei, we do everything together into one big thing, which we'll do at the end of this class. And when we put everything together, we can formalize this because we're going to think about the nuclei and the electrons together. But the important thing is to know, and this is for near, is that we can treat them separately. Right? We can focus in on either one and learn about the physics of a molecule from two different perspectives, the motions of the nuclei versus the motions of the electrons. You've been doing this work, this kind of assumption, your entire collegiate career as a chemist. Because when you go to spectroscopy, when you do spectroscopy in organic lab, you do UV vis. Right, you're exciting electrons and molecules with ultraviolet radiation. Right? So the electrons are moving on their energy level difference is on the order of a visible photon. That's a high frequency, right? Remember, it's a short wavelength, high frequency, right? So the motion that's exciting is very fast. And where do the absorptions from the nuclei moving show up? Well, they show up in the infrared, right? Vibrations. Right? And those are much shorter, longer wavelength, right? The wavelength of a vibration's on the order of a micrometer, whereas the excitations of electrons are on the order of 100 nanometers. So you've got a factor of 1,000 difference in energy between the two motions, and therefore a factor of difference in momentum or speed, factor of 1,000. So you've been using the Born-Oppenheimer approximation every day. The fact that you can use different energy scales, NMR is in a radio, infrared is vibrations, UV vis for electronic, and so on. You've been using the Born-Oppenheimer approximation your entire career, you just didn't know it. If this wasn't true, if the nuclei moved at the same rate as the electrons, you wouldn't have infrared spectroscopy and UV vis and NMR. Everything would be coupled. And so when you excite something with an infrared photon, you'd excite the electrons and the nuclei together in some mixture. And then when you go to UV vis, all hell breaks loose. You've put so much energy to it, everything's moving. Right? How do you interpret that? When you have 100 objects in your molecule, you got 100 electrons and a couple of nuclei. How do you interpret that physics? Well, the advantage is that they move at different scales, so we don't have to worry about that. Everything splits out. Right? This is why we have different levels of spectroscopy, different techniques for different energy levels. They probe different motions in your molecule, and this is because of the Born-Oppenheimer approximation. Right? So it's very, very powerful. It's ubiquitous in chemistry, but it's often not mentioned explicitly. But this is a very real thing, and we can prove it mathematically. But we'll come back to the proof later. What I want you to understand is that we don't have to worry about, if we're going to think about bond stretching, we can worry about the electrons later. That's a hard problem. There might be a lot of electrons in my diatomic molecule. But in the end, I have two nuclei moving away from each other in a diatomic molecule. Let's worry about that, the vibration, right? The physical motion of the bond. So that's what we're going to be looking at today, is bond vibrations. All right, so we're going to be looking at vibrational motion in a molecule. Right? And all vibrational motion is the motion, the relative motion of nuclei. Okay? The relative motion of nuclei. We're not even going to think about electrons. We're going to ignore electrons now. Think about the motion of the nuclei. The really nice thing about this is that this seems like an aside because we've been talking about electrons the entire class. The technique that we're going to be doing for this is ubiquitous. You know, when we talk about in physics, we talk about spheres and spherical cows and these really, really simple toy models. This harmonic oscillator approach we're going to do for vibrations is applicable to more than just vibrations. The harmonic oscillator is the microscopic physicists or the microscopic chemists equivalent to a spherical cow. We use harmonic oscillators and springs for everything. It's usable for everything. It's so useful. It's a very, very powerful technique, and so it's really good to learn it, I think. And it's useful for more than just anything that vibrates, anything that oscillates like this. We can use a harmonic oscillator approach to solve. There's lots and lots of applications of this. Crystals, solids, powders, single molecules, magnets, the electric field. We can treat the vacuum, space, as a collection of harmonic oscillators, where each oscillator, when it oscillates, it emits a photon. And you can show that you can rederive all of Maxwell's equations from that assumption. Right? That when you treat every little piece of space as an oscillator that emits a photon if it's excited, you can derive all of physics from it. Right? So we use this technique all the time. But I'd like to introduce to you in the most chemical way possible, which is vibrations. So this is how we're going to do this. So we're going to take our two atoms, and we're going to connect them with a spring. All right, you can think like a slinky. All right, and we're going to say that at any given point, the length of that spring is L. All right, so we have two masses, M1 and M2, and you have a length of a spring L. Okay, so just think of slinky. Right. And we're going to define L. What we're going to do is I'm going to put it this way. What we're going to do in our molecule, right, is we're going to change L. Right, we're going to stretch the molecule. We're going to shorten it. Right, we're going to stretch the spring or compress the spring and see what happens. Right, so I want to define a coordinate. Define displacement as delta L, which is the current length of the spring minus some fixed length, the equilibrium length of the spring. Right? And this is the length of the spring if you let the spring just rest and you don't put any energy into it. Right? Every spring has kind of an average length that it likes to be. Right? Imagine that you have, for instance, you have the spring connected to the ceiling, and on the bottom of the spring, I can just draw it. Right? Imagine we have a block like this, and connected to it is a spring with a mass. Okay? And we don't do anything to it. We just leave it at rest. All right? And the length of the spring at rest is L naught. Okay? So every spring has an average equilibrium length, right? You can have really short springs, really long springs, and so on and so forth. Okay? So that's a good way to think about it, right? That you just hanging a spring. Now that has gravity involved, right? So let's avoid gravity for a second. So imagine you have this in space. And there's no gravity pushing it down. You just put a mass on a spring and you just let it rest and no gravity. Right? And that's the equilibrium length of the spring. Okay. For a slinky, for instance, the equilibrium length, once you put it depends on the size of the mass you put on it, but a slinky is about a meter, roughly, a couple feet. L0. A typical slinky you buy at the store. Okay, so what I want to think about is what happens to I'm going to stretch my molecule out, right, and I'm going to let it go. Right? I want to think about what are the physics of the bond, the physics of that motion once I stretch it and let it go. All right, so I'm going to do this classically. Right, so how do we do it classically? Well, all we're going to do for classically, we're going to use, so let's solve this classically. Right? And when we solve things classically, we use Newton's second law. Newton number 2, right? Which is F equals ma. Or force and acceleration are vectors. We won't have to worry about that eventually. Right? F equals ma. All right, so we have two things that we have to answer here. First, what's the force? All right, so we're going to stretch this spring out. There's the spring, if we stretch it past L naught, right, we displace it, positive displacement, we stretch it out. The spring's going to have some force acting against you to compress, right? It wants to come back to equilibrium, right? So there's some force associated with it, all right? And for springs, we're going to use the simplest approximation for a spring, which is called Hooke's law. You guys may have learned this in Physics 1, which says that the force of the spring is minus some constant k times the displacement, delta L. Okay, and k is a number. This is called the force constant. All right, and every spring has a force constant. All right, it tells you something about the stiffness. All right, so large K, stiff spring, and small k is a floppy spring. Okay, so a slinky, for instance, a slinky has a very small k. Right, slinkies are very easy to stretch, and when you stretch them too far, they kind of lazily come back. Right, they're very, very floppy springs. But if you think about the springs, for instance, that open and close the valves of your car engine, those are really, really, really stiff springs and have really, really strong returning force. Right, so those kinds of springs have very, very large K. So it's just a function of, so the spring has two features, right? So the spring has an equilibrium length, right? This is a property of the spring. And it also has K, the stiffness of the spring. Okay, so the spring is parameterized in two different ways, the stiffness and the length. Okay, so this is nice, right? This says that the force is dependent linearly on the displacement. So let's put that into F equals ma. Now, what is acceleration? It's probably easier to think, again, acceleration, let's do it the proper way, which is that acceleration is the second derivative of position with respect to time. Right? Remember, velocity is the first derivative, acceleration is the second derivative. All right, so by putting that together, we can calculate the motion of this spring using F equals ma, but here's the problem. Our system is dependent on two coordinates, the position of m2 and the position of m1. Right? So if I were to put them on an axis system, like x, m1 is at x1, and m2 is at x2, right? Which would mean that the displacement is x2 minus x1 minus L naught, because the length is the difference between those coordinates. I have two atoms moving independently with each other, right? I could fix m1 and move m2. I could fix m2 and move m1, but I can also move them together, right? So I have two accelerations, two forces. I have the force on m1 and a force on m2. Right? So when I put all of this together, I have the mass of m1 times its position acceleration, which is the second derivative of x sub 1, its position with respect to time, is equal to the force, which is minus k x1, its displacement. Maybe we could write x1, well, we could write it as delta L. Sorry, I'll write it as delta L. No, it's x1, so we'll call it x1. And we also have m2 dx2 dt squared is equal to minus kx2. Right, so I have two differential equations I have to solve. All right, so that's the problem, because it loses the point of our system and to begin with. what we care about is not the motion of the atoms, but the length of the spring. Right? We really only have one coordinate. It doesn't really matter where M2 and M1 are with respect to each other, because you can always draw a line between them, right? The spring always connects those 2 points. So it doesn't really matter how mass 1 moves relative to mass 2, because you can think if you change your frame of reference, moving x1 with respect to x2 is basically the same thing as stretching or compressing this bond in some direction. All right, so this, even though this looks like a two-dimensional problem, 2 different formulas I have to solve, it's actually 1. I just have to rearrange things, and I should be able to get in a single F equals ma equation that's proportional just to the length of the bond. All right, that we can measure the force acting on the bond just by the length. All right, so we got to do something with this and reformulate it so that we only have 1 coordinate instead of 2. We don't have to worry about the atoms, we just worry about the bonds. All right, so how do we do that? Well, again, this is like classic physics 1. Right, so the solution is the shift to center of mass frame. Okay, remember that the momenta are conserved, right? So the momentum, that's rho, sorry, so the momentum of 1, atom 1, plus the momentum of 2, which is going to be m1x1 plus m2x2, is equal to 0. Right? The momentum between the atoms are conserved, right? Momentum is always conserved. Right? So that means that when I move x1, x2 is going, the second atom has to move as well. All right? To conserve momentum. So I can use Newton's third law. So Newton 3 then concludes, right? Newton 3 is every reaction has an equal and opposite reaction, which says that the second derivative with respect to time of the sum of the momenta is equal to 0. Okay? So the useful part about this is that we have a conservation. If we stretch one atom by a certain displacement, the other one has to move in ratio with it, up to the difference of the masses. Okay, so if M2 is really big, so if M2 is way bigger than M1, and we move mass 2 away from mass 1, say by some unit 1, like some unit x, if M1 is smaller, x1 is going to be much larger, right? So if we move in this frame atom 2 by a little bit, and atom 1 is really small, atom 1 is going to move a lot. Equivalent in this frame. Okay, so we have what we call mass-weighted coordinates, right? A heavy atom that moves a little bit is going to be compensated by a light atom that moves a lot, and vice versa. Or if they're both the same, I move one atom, the other one moves exactly the same in the opposite direction. Okay, so what we can do is we can define a fixed coordinate, which I will call big X with a CM, which means the center of mass coordinate. And XCM can be written as M1x1 plus M2x2 over the sum of the masses, like that. All right, so what I'm going to do is I'm going to, this position right here, the center of mass of the molecule, doesn't move when I stretch the molecule. It's a fixed point. That's the point of the center of mass. It's like a fixed reference point. So what can I do then is if I stretch one atom, stretch the bond, that displacement of the bond I can represent as displacement of the atoms with respect to the center of mass. The center of mass is fixed. So if I know the distance between an atom in the center of mass and another atom in the center of mass, I know the distance between the two atoms. So I can relate both of the displacement with respect to the center of mass. Right, so I'll just draw that. Right, so here's M1. Here's M2. All All right, let's assume that M2 is greater than M1, so it's bigger on the right side. And that means that the center of mass is going to be somewhere closer to M2. Here's the middle of the molecule. That's right, it's the fulcrum, right? You can think about like a seesaw, right? A seesaw, center of mass of a seesaw is dependent on what the masses of the people riding it are. So if you've got a big person on one side and a little person on the other side, the fulcrum is going to be closer to the big person. Right, we'll do the same thing. Right, and so when I displace the atoms, when I move M1 or M2, so if I move M1 in this direction, M2 in this direction, right, I can always measure the displacement of those atoms with respect to the center of mass. Right? And so if the atoms are moving equal and opposite to each other, if this atom is moving away from the center of mass and this one's moving away from the center of mass in that direction, we don't have to worry about the coordinates of those two atoms. The only thing we care about is the difference, delta L1 plus delta L2. That's the total displacement. Right? From here, delta L total is delta L1 plus delta L2. Right? So this sum is always there. It's always moving, and right, so instead of thinking about each of the atoms moving separately, let's just think about the motion of the total displacement instead, relative to the center of mass. Because if this atom moves this way, away from the center of mass, this one's going to move equal and opposite to satisfy this expression. And so if one moves, the other one moves, and so the only thing that's actually changing is the bond length. You just represent it as the bond length. So I'm going to do physics magic here. And the equivalent way to write this, or an equivalent problem, right, this gives you the same physics. Once you do this shift, is that the bond problem is equivalent to having a brick wall, and attached to it is a spring attached to some mass, right? With so the length of the spring, of course, delta L equals L minus L naught. And the mass of this spring is mu. We call mu, which we call the reduced, which we define as the reduced mass. And mu is equal to M1 plus M2. Oh, sorry, I have that wrong. Sorry. It's M1 times M2 over the sum of the masses. M1 plus M2. This is the reduced mass. So what we've done by shifting to the center of mass frame is that we've reduced a problem that has two coordinates to a spring with a single mass fixed to a fixed point, right, our wall. Same spring, same stiffness, same length. But what we've done is we've rescaled the mass to be kind of like an average mass of both of the atoms. And kind of think of this as an average effective mass. All right, so now our physics are only dependent on the length of the spring. Right? This is a fixed wall. This is never moving. This is the thing that's moving. And so now the physics, the force applied from the stretch is only dependent on the displacement of one variable. Right? So we can write very quickly the new version of Newton's law for this. And I just want to make sure I get all my units, my notation correctly for you guys. Yeah. You get that, so Newton's law, so Newton 2 now. Is this effective mass, mu, F equals ma, so we have m, which is mu, times a, which is the displacement of the bond, dl dt squared, is equal to minus k, L minus L naught. Okay, so again, we still have F equals ma. Mass times acceleration is equal to the force. Right, but now we just have one coordinate, right? It's just the bond displacement. Right? So every time we talk about a diatomic molecule and we talk about it moving, we're never going to talk about the individual atoms. We're going to talk about an effective system that's equivalent, where the two masses have been merged together into a single ball. It's an equivalent problem. Right? So you will always talk about reduced masses in this class because of this. Okay. So what are the solutions to this problem? I'm just going to rewrite the equation. So what I'm first going to do is I'm going to write x. I'm going to redefine my coordinate to x equals L minus L naught. Right? That just makes my math easier. And I'll show you why in a second. All right, and so my equation, my Newton's law equation, is now mu times the second derivative of position with respect to time is equal to minus kx. Okay, so I'll rewrite this. It says that the second derivative of the position with respect to time is equal to minus k over mu times the position. Okay. So we have a differential equation to solve. We want to solve for the position. The position, again, is a function of time. So I'll just put that explicitly in there. Right? It's a function of time. So it says that the derivative of the trajectory, the second derivative of the trajectory, right, the second derivative of some function is equal to the function times a constant. We saw this for the particle in the box. Right? This is the exact same formula as d squared psi dx squared is equal to E psi. Of course, we had different variables, but this was the equation that we solved for the particle in the box. Right? Since the second derivative of the wave function gives you the wave function back times the number. Harmonic oscillator is the same. The second derivative with respect to time gives you the function times a constant. Right? Well, we know the solution to that, right? Sines and cosines. Right? That's what the solution for the particle in the box is. It's exactly the same expression. You just have a negative sign here, a negative constant. It's the same equation. Same differential equation, same form. Right? So the solution to this expression is that the trajectory of our spring, right, the position of the spring as a function of time, is some constant a times sine of frequency times time plus b cosine omega times t. And the frequency of this wave is equal to the square root of the stiffness divided by the mass of the atoms. This is the general solution. All right, we haven't determined A and B yet, but remember the way we determine these in the particle in the box is we considered the boundary conditions of the box. In this case, whether it's sine or cosine depends on the initial conditions of our spring, whether it's at rest at the beginning or we've stretched it. We can look at that in just a second. But the point is that this spring, so let's imagine I stretch my spring all the way down and I let it go. It's bouncing up and down like this, right? The way that the position of the mass oscillates is like a cosine or a sine. Sine goes like this, right? And the frequency at which it goes is entirely dependent on the mass of the object on the spring and the stiffness of the spring. Right? So the frequency at which the spring oscillates is entirely dependent on its physical parameters. All right, we call this the there's a lot of different terms for this omega. Sometimes we call it the fundamental frequency. Right? That's what we'll often call it, the fundamental frequency. And the way to interpret this fundamental frequency is, there's a couple different ways to think about it. But the way I like to think about harmonic oscillators is to think about a piano or a guitar string. So in a piano string or guitar string, the string is fixed to 2 points. Right, so we have, let me just do that again, right? So we have 2 points, right? We have 2 parts for our string. And we tie a string around these parts. Right? And the string has some length. Okay? Right? And when we pluck it, okay, we can pluck it at any frequency or any energy we want, but there's a specific set of frequencies that we pluck, that when you pluck the string, the wave that propagates through them, right? So imagine I pluck that string and the string oscillates like this, okay? And the fundamental frequency of the string, so the FF for a string, for a guitar string or a piano wire, is where the length is proportional to pi over L, or pi. Proportional to some factor of pi. What does that mean? Well, that means that when the wave starts from here and ends here, it either goes through one whole period or one whole period or a half period. Right? So the fundamental frequency looks like this. It has a frequency such that the wave goes through exactly half of its phase in length L. Right? So you can think of this as the pi point. Right? So this is the fun, right? And so what happens if this wave starts here and propagates this way, and it hits the other end, it bounces back, right? It oscillates back and forth. And how does it oscillate back and forth? Well, the wave amplitude increases as it travels along the wave, right? And then it hits the end of your string and then bounces back. It reflects. And how does it reflect? Well, it reflects in exactly the same way that it came, right? Because you just go from pi to 2 pi, but backwards, right? So when this happens, you have constructive interference, which we also call resonance, right? And that's the condition where you've plucked the string at the right frequency, that it bounces back and forth without destructively interfering. Okay? And so what is the classic way that we tune our resonance frequencies? Well, what's the definite for Western music? What's the definition, right? The definition of the fundamental frequency, if you will. So Western music. The fundamental frequency is, I don't know what you would call it, but it'd be the A in the first octave. We'll call it A1 or whatever. I don't know what the actual notation is. Someone could tell me. And this is at 440 hertz. Right? So an A string is one whose tension and length is such that when you pluck with a displacement or a motion that's 440 hertz, that you complete half a phase of your cycle. You get constructive interference, right? And what do we do when our strings are off and they're not A, B, C, D, or they're not playing the notes that you want? What do? We tune them, right? And on a guitar, right? We tune them. And what do you do when you tune a string? Well, you wrap the string further or loosen it round the post, which increases the tension of the string, which increases the stiffness, right? So when we're off tune a little bit, right? We want our string, we want to have our fundamental frequency to be exactly A on our A string, or some octave of it. Maybe we don't want 440, maybe we want a different octave, right? Depending on your tuning. But if we're off a little bit, and we strum and we don't get 440 hertz, the exact resonance frequency of the string that we want, then we tune the K of the string by making it tense or weak, less tense, in order to get omega to be exactly 440 hertz. Okay? And how do we get harmonics of that wave, right? How do we go to the next octave? Well, what's A2? 880, right? You double the frequency. What would that mean? Well, at 440 hertz, if it only creates one half phase, goes through one half phase as it travels the wave, or the string, then at A2, the second octave of A, it would complete one whole phase. Right? So if this is A1, then in green here is A2. Right? And what do we call A2? Well, we call 440 the fundamental. And we call 880 the first harmonic. Right? Right? And there's other harmonics, right? We go up an octave, we go to the second harmonic. Right? That would be a wave that completes a period and a half along the wave, the length of the string. Then we go to the fourth octave, the next harmonic, that would complete 2 periods of the wave on the string. Right? And all we're doing when we tension the string is just changing K. Changing omega by changing K. Okay, so springs work precisely the same way. Just in a spring, we're not tuning the tension of the wire, and it's not a fixed length, but rather what we're doing is we're allowing the tension to be the stiffness of the spring and also the mass that's hanging on it, and we're moving the length of the string. But the way that the length of the string moves, the physics of that is precisely the same, has the same solutions as resonance on a fixed wire. Right? And so you only get these fundamentals and these harmonics. Right? This is why we call it a harmonic oscillator. Right? A spring with a mass attached to it, or a taut guitar wire, these are called harmonic oscillators. And why are they called harmonic oscillators? Well, first of all, they oscillate like a sine wave. And why are they harmonic? Because the only solutions of them are the fundamental frequency and its harmonics. The only stable oscillations of your spring or constructive oscillations of your spring or your guitar wire is the fundamental frequency and its integer multiples. Right? That's what we mean by harmonic. That the allowed frequencies of your spring are integer multiples of each other. Right? So if omega is 10 hertz for a bond, then the allowed frequencies of the bond are 10 hertz, 20 hertz, 30 hertz, 40 hertz, 50 hertz, 60 hertz, and nothing in between. Same idea here with the taut guitar wire. Right? If you strum a guitar wire at a certain length with a different frequency that isn't a harmonic, then you get destructive interference. Right? I'll just kind of show you that. If right here, I'll just draw it here, right? If this would be a 1, 2, 3, 4, a fifth harmonic of our wave. What if we did it something that looked like this instead? All right, what if the wave kind of goes like this, and it hits the wall, or the wall at some random part of its phase, and then goes back? Well, it's going to be kind of off sync from the previous one. Sorry. It's going to be like this instead when it bounces back. Right? And when you add those waves contributions together, the bounces, they destructively interfere and cancel each other out. Right? So the only strong sounds that you get out of your string are the harmonics of the fundamental frequency. Otherwise, you get destructive interference. Okay? So that's what I mean by harmonic. Right? The bond in some ways has a fundamental note. Every bond has a fundamental note that's dependent on its stiffness and the masses attached to it. And the allowed frequencies of that vibration, that oscillation, are the harmonics of that frequency. Right? 2 times that frequency, 3 times, 4 times, 5 times, right? Integer numbers. Remember, everything has to be quantized, right? I'm not even talking about quantum mechanics yet, and we've already started to see quantization appear. I'm saying that the allowed solutions of this formula are integer multiples of a number. Integer multiples of a frequency. Remember, frequency is energy in quantum mechanics. E equals h nu. So that means we know that something in there, once we figure it out, the energy is going to be quantized in the same way that the waves are. Right? This is what's called a harmonic oscillator. Right? So anything that oscillates like a sine or a cosine, just a pure sine or cosine wave, and it's moving between two bounds, stretching and compressing, or moving, stretching, or oscillating on a fixed axis, fixed length, or whatever, and these are harmonic oscillators. Right? They're very, very powerful because lots of things oscillate. Remember, quantum mechanics is about waves. We have lots of waves, lots of things propagating like waves with frequencies in quantum mechanics. It's not surprising if we come up with the classic harmonic wave solution that it's going to be useful. All right. All right, so this is kind of all I want to say about harmonic oscillator. I'm going to post a little web app for you to look at over the weekend, just like 2 seconds. You can use it on your phone. It's a simulator of a classical harmonic oscillator. So you can see how, when you stretch the spring, how it oscillates in time. You can look at the oscillation frequency. You can change all sorts of different things about it, and you can kind of see how it works. Right? Not so worried about the math. The important thing about the math is that we have some sort of natural quantization. That there are these allowed frequencies that are an integer multiple of the fundamental frequency, which is dependent on the spring or the stiffness of the wire or the bond. All right, that's really what I want to take home from this, and this quantization and the equal spacing. Right, 1, 2, 3, 4, 5, 6. Those are the things that we need to keep in mind. And if you have a Slinky at home, you can do all of this at home. It's really easy to see all of this visually. Okay, so that's the classical harmonic oscillator. So let's start to think about quantum a little bit. Let's get ourselves set up. Okay, so we have classically this cosine sine solution where omega is dependent on the stiffness and the mass of the molecules. Right? And we also have that the force is equal to some constant, the stiffness times the displacement. All right, so this is all Newton's laws, right? This is just Newton's laws. Right? But we're not doing Newton's laws in this class, so ultimately we need to do quantum mechanics. Right? And so what does quantum mechanics need? Right? What do we need for quantum mechanics? Well, we need to solve the Schrodinger equation. Right? Ultimately, that's what we have to do. All right, so we have a different equation we need to solve. I'm going to stop using this pink. I'm sorry, it's really hard to see on the screen. It looks really good on here. So we have to now think about the perspective of quantum mechanics, which again is coming up with a Hamiltonian, our operator for our spring system. All right, but all we have, right? What does the Hamiltonian have? Well, the Hamiltonian's two parts. It's kinetic and potential. Okay, so we have to figure out the kinetic term and the potential operators for this system, right? And so we got a little bit of work to do. All we have right now is a force. So let's first tackle kinetic energy. Well, remember that kinetic energy classically is proportional to 1/2 mv squared. All right, and that of course is going to be 1/2 times the reduced mass times the change in the displacement with respect to time squared. Right? And we can rewrite this as the momentum squared of the string divided by 2 mu. All right, this is what we did for the particle in the box. Nothing's changed, right? 1/2 mv squared is always the same for everything. All right, so how do we write? So we don't have to do anything new for kinetic energy. We could just write it the same way we did for the harmonic or for the particle in a box, which is h bar squared over 2 times the mass, which is mu in this case, times the second derivative with respect to the displacement coordinate, x. All right, we're done. That's it. Right? Every time we do a new problem, we're going to have to come up with a kinetic energy. but the kinetic energy of everything's the same. It's 1/2 mv squared or p squared over 2m. So if we know the mass, we know the operator. Right? So we're always going to see this term in our problem. And this is, again, what I told you last class, is that all particles move like this. The thing that determines the difference between different systems is the potential. Right? What kind of environment is our system in? And so we have to come up with a potential energy. Right? And that's what's going to define our system. That's what's going to make this different than the particle in the box, is V. Right? So how do we calculate V? Well, there's a formula. The definition, this is not the best definition, this is not the definition that you always get for force in physics, but it's the proper definition of force, which is that, I'm just going to write it here, that force is equal to the negative derivative of the potential energy with respect to position. Okay? So how the potential energy changes as displacement times -1 gives you the force. Right? So the force is directly related to the potential. This is a great formula to remember. I don't know if you guys learned this in physics, but when I learned it, it changed my life because it makes everything so much easier. I'm going to erase this stuff about kinetic energy here, just to give myself a little more space. All right, so if force is the derivative of potential, that means then that the potential, so function of position, is the integral, well, minus the integral of the force. Okay? So all we have to do is integrate the force. All right, well, that's easy. All right, that means that V of x is equal to minus the integral of minus kx. X dx. Right? I'll factor out the k and the negative signs. Right? And the potential of this force is just the integral of x dx, right? Which is 1/2 kx squared. Right? The integral of x is 1/2 x squared. Right? So our potential energy is done. We know it. It's a parabola. So V, the potential function, or the potential operator, is just 1/2 kx squared. So, put this all together. Hamiltonian is our kinetic energy minus h bar squared over 2 mu times the second derivative with respect to position plus 1/2 kx squared. Okay, so now you can see the difference between the particle in the box and the harmonic oscillator. The kinetic energy is precisely the same. It's still we're still treating it like a particle or a wave moving in space. That hasn't changed. But what's happened is the space in which the system is allowed to exist in. And the particle in the box, this term was 0. There's no potential, right? Because it's free to move as it pleases inside the box via 0. But here we have a function that's a function of position. What does that mean? It means that as you stretch the bond or compress it, it's squared, right? So remember, x can be negative or positive. Negative means compression. Positive means expansion, stretching. Right? It says that the energy of stretching goes up as you either stretch or compress away from equilibrium. Right? So remember, in the particle in the box, what does our potential look like? So in PITB, pain in the butt, our x-axis with respect to potential on the y-axis is just 2 infinitely high walls, and the potential is 0 between them and infinite outside. Right? We just have a square well, right? But in the harmonic oscillator, which I'll write HO here, pain in the butt and ho, we have something that isn't square anymore. our particle now exists in a space that looks like this. Or that's L naught, sorry. I wrote that as L naught. Right? So we have a different structure to our box. Right? Instead of having 0 everywhere and then 2 walls that are infinitely high on the edges, right, a finite space, we have a space that slowly and continuously grows to higher and higher energy as we move away from it. Right? Very different. Right? And what does that mean? Right? So, for instance, if, for instance, the energy, imagine the energy of our electron is right here. Right? Imagine the electron's at this energy. How much energy does it need to get over the box? Well, it's infinite. Right? It's infinity over here. So there's no probability to go outside. But what about here? What if my system is here at this energy? Well, there's nothing that says that the potential out here is infinite. It just says that the energy is slowly increasing as I stretch. Right? So as I stretch, the energy increases, but it doesn't go to infinity. Right? So very different. We have a finite bound that's energy or position dependent versus one that's fixed and it's infinite. Right? So we're going to have different physics. Not only is the shape different, of course the shape is important here. Right? You have a parabola versus a square box. But the fact of the matter is that if I go to the edge of the box at some energy, if I stretch the bond a little bit, it doesn't go to infinity in energy. It just increases a little bit. Right? Whereas here, if this is a bond, and my bond is right here, right? My stretching's right there, and I want to stretch it a little more, I can't. Right? Because the energy out a little further is infinite. Can't stretch it any further than that. But here, if I'm at this energy and I want to stretch it a little bit, well, I'm just going to kind of climb this slow energy curve a little bit. So the change in energy as I stretch it past that limit is finite. Right? You're going to get different physics. Very, very different physics. Everything's going to look very different. Still going to oscillate, still going to integrate to one. Wave functions are still going to do everything we like, but they're going to look different and they're going to act different. Because this is in some ways, a pliable wall. Right? This is a wall that's position dependent. And it doesn't go straight to infinity. It only goes to infinity as x goes to infinity. Right? X has to be infinite for the energy to be infinite. But here, x can be finite, the energy is infinite. Very, very different world. Right? So we're going to see different physics, different properties. Right? It's a completely different system. All we've done is we've gone from a square box to a parabolic box, and that's going to change a lot. All right, so let me just write one more thing. You know what? Let me not write any more thing. I think that's a good place to stop. Let me just kind of summarize things. So by going to this spring system, again, same physics, we're still going to do the same process. We're going to find wave functions that satisfy the Schrodinger equation for this Hamiltonian. We're not going to do that math explicitly. Right? I'm going to set it up for you, and then we'll realize it's a tough problem, but it's a solvable problem, and I'll show you the solutions. All right? It'll be a little trickier to come up with some wave functions that satisfy this. But we can come up with them. We can come up with exact solutions. I can tell you the exact energies and the exact wave functions for all the states of this system. We'll be able to do that. And we're going to find that it's an incredibly good, almost perfectly precise theory for molecular vibration. Right? It's going to give us everything we need to know about molecular vibration. And when we realize that there are some problems, it'll give us the solution on how to fix those problems and improve things. Okay? All right, so this is our first foray into a real physical system, something that's plausible. Right? It's implausible to have an infinitely high box. But it is plausible to have a spring that stretches. So we'll start looking on that on Tuesday, guys. All right, have a good one. I will upload this today for you guys. I guess I'm sticking with this app for a while until I figure out otherwise.
I don't feel like this one.
So in the other room in Maxie, that room's really hot. My computer throttles and it shuts the software down and it crashes frequently. So sometimes I have to sit there for like a couple minutes to get everything started back up in the middle of lecture. So I'm trying to find a better way to do that. But I haven't found it yet. This isn't too bad. It's really good in this room. What I need is like Abby to come with like a fan to blow my computer. I need her to do that for me.
I was told to show you